In this video, we're going to talk about position and velocity, and we're going to begin with an example. Suppose a car is stopped at a stoplight, and the light turns green at time t equals 0 seconds, and the car starts moving forward. And suppose the distance traveled by the car in meters during the first 4 seconds is given by this function, f of t equals t squared. So what this means, for example, is that when t equals 3, after 3 seconds, the car has traveled 9 meters, 3 squared. When t is 2, the car has traveled 4 meters. Oh, when t is 0, it's of course traveled 0 meters. So let's look at this in a diagram here. What we've really drawn is an axis here. We can kind of think of this as like a y-axis, and we can plot the position at various times t of where the car is along this y-axis. Now remember, our formula is f of t equals t squared. So f of 0 is 0. So notice that time t equals 0, we are at the position 0, right? The car hasn't moved yet. We're just at the initial position. And when time t equals 1, we've traveled 1 meter. But at time t equals 2, we're at position 4 here. We've traveled 4 meters. At time t equals 3, we are at position 9 along this number line here, along this axis. So notice it seems like the car is speeding up. It's accelerating. In fact, it is. Notice in that first 1 second, it only traveled 1 meter. But in the second, between t equals 1 and t equals 2, it traveled 3 meters. Okay, between t equals 2 and t equals 3, it traveled 5 meters. So the car appears to be speeding up. It's accelerating. Now, if we wanted to find like the average velocity of the car between, let's say, t equals 1 and t equals 3 seconds, we'd have to figure out, well, how far did the car travel? Notice it traveled 8 meters in that 2-second interval. So between t equals 1 and t equals 3, it traveled 8 meters, and it did it in 2 seconds. And 8 divided by 2 is 4, so it traveled 4 meters per second on average. That was the average speed, or the average velocity between t equals 1 and t equals 3 seconds. But what if we want to find the instantaneous velocity? How fast the car is going exactly at, say, t equals 3 seconds? How could we do that? Now, in Desmos, I've graphed this function f of t equals t squared. And notice that our car is moving along the y-axis here, but I've allowed a t-axis here to be a horizontal axis. So we can actually watch the car move. So notice at t equals 1 second, the car is at position 1 along the y-axis. At t equals 2 seconds, we're at 4. T equals 3, we're at 9, and so on. In fact, I can play this here. And notice the car appears to be accelerating, right, as time moves on. So time is moving here at a constant rate. Let me hit play. 1 second, 2, 3, 4, right? The car is moving. Let's do that again. So notice t equals 1, 2, 3, 4 seconds. The car is accelerating this way. Now, again, if we wanted to figure out where the car is at 1 second, we'd be at 1 meter. And at time t equals 3 seconds, we're at 9 meters. If we want to find the average velocity between that in that 2-second interval, we'd have to find the slope of this secant line, right? Notice the slope of this secant line between 1, 1 and 3, 9. The run here would be 2, right? That would be that 2-second interval. The rise would be 8, right? Because it traveled 8 meters in those 2 seconds. And when we calculate the rise over the run, we get 8 over 2, which is 4. So it traveled 4 meters per second in that 2-second interval. Now that's the slope of a secant line. If we wanted to figure out exactly how fast the car is moving at time t equals 3 seconds, what we need to do is find the slope of the tangent line at time t equals 3. Okay, so let's recall the function here is f of t equals t squared. So the derivative would be 2t. If we want to find the slope of the tangent line there at 3, we'd have to find f prime of 3. And notice that f prime of 3 is 6. We just plug in 3 right here. 2 times 3 is 6. Okay, so what that really tells us is that at time t equals 3 seconds, the velocity of the car is 6 meters per second. And we say the velocity, or the instantaneous velocity, to kind of distinguish it from the average velocity. The instantaneous velocity, how fast is the car going at the instant that t equals 3 seconds? The car is going 6 meters per second. So notice the derivative gave us the velocity, or gave us the instantaneous velocity. So we have this. Suppose an object moves along the y-axis so that its position at time t is given by y equals f of t. So in our example, f of t was t squared. Then the instantaneous velocity of the object at time t equals c is given by f prime of c, the derivative of f at c. Now, I should tell you here, I've been using t for time. The book and MyMathLab sometimes uses x for time. So it'll just use f of x, and x will be the time variable. So x will be in seconds, let's say, or in hours. In fact, let's do two examples, and these examples are straight out of MyMathLab, the homework from MyMathLab. Suppose an object moves along the y-axis so that its location is y equals this function here, f of x equals x squared plus 5x at time x, okay, where y is in meters and x is in seconds. Find the instantaneous velocity at x equals 3 seconds. Okay, so what we really need to find is what is f prime of 3. Now, f of 3 is going to give us something, but that'll just tell us the position of the object along the y-axis. But f prime of 3 is going to tell us the velocity. So what's f prime of 3? Well, f prime of x would be 2x plus 5. Okay, the derivative of x squared plus 5x, 2x plus 5. So f prime of 3 would be 2 times 3 plus 5. So that would be 6 plus 5, which is 11. So our answer is 11 meters per second. That's the velocity at time x equals 3 seconds. Okay, let's look at another example. Again, this is straight out of MyMathLab. If an object moves along the y-axis marked in feet so that its position at time x in seconds is given by f of x equals 182x minus 13x squared, find the following. Okay, what is the instantaneous velocity function? And they're using the letter v for the velocity function. So v is just f prime of x. You could think of it as v of x, right? V of x, the velocity at time x, is just f prime of x. Okay, also, what is the velocity when x equals 0 and x equals 3 seconds? And also, what is the time when the velocity is 0? Okay, so this is not saying the time is 0. It's asking at what time is the velocity 0? Okay, so let's answer this question. So remember, our function f of x, let me write it down here, f of x was 182x minus 13x squared. Okay, so what is f prime of x, right? F prime of x is going to be 182 minus 26x. Okay, the derivative of 182x is 182. Derivative of 13x squared is 26x. So that's our v of x. Remember, v of x was just f prime of x. It's 182x minus, or 182 minus 26x. So that's what you would type in to MyMathLab for this problem. Okay, now the velocity when x equals 0 seconds is what? Well, here's the velocity at x seconds. What's the velocity when x is 0? So we just need to find v of 0. So notice v of 0 would be 182 minus 26 times 0, and that's just 182. So the velocity at time t equals 0 seconds, or x equals 0 seconds, would be 182 feet per second. Okay, it's at time x equals 0, the object's already moving, right? It's already moving at a rate of 182 feet per second when x is 0. When x is 3, what is it? Well, we need to find v of 3. Okay, so we get 182 minus 26 times 3, right? We're just using this formula here. And we get 182 minus, I believe that's 78. And 182 minus 78, I believe, is 104. So this would be 104 feet per second. So again, you'd type in 104, and that would be the velocity in feet per second. Okay, now this last question is not asking you to plug in 0. It's saying, in fact, what is the velocity when x equals 0? It's 182 feet per second. This is saying, at what time is the velocity 0? So if we have this formula here, in other words, what value of x can we plug in here that will make the velocity be 0? Okay, what x value would make this output be 0? So what we need to do is solve the equation 0 equals 182 minus 26x. Okay, we need to solve that for x. So we want the velocity, which is this, to equal 0. Okay, so what we can do is add 26x to both sides. We get 26x equals 182. Then divide both sides by 26. And when you work this out, I believe that's 7. Is that right? 140 plus 4. Yeah, I believe that's 7. Turns out it's exactly a nice number. Now, what would that be? Would that be 7 feet per second? No, that's just 7 seconds. At time t or x equals 7 seconds, the velocity is 0. Okay? V of x gives you this formula, so you can find the velocity at any time x. So when x is 0, it's going 182 feet per second. When x is 3, it's going 104 feet per second. When x is 7, it's actually going 0 feet per second, right? It's the velocity is 0. It's actually stopped at that instant when x equals 7. So notice what we have here is really two different interpretations of the derivative. We could think of the derivative, f prime of a function, as a function whose value at x is the slope of the graph of f at x. So we think of a derivative as the slope, or the slope of the tangent line. That's how we initially started thinking about derivatives, was in terms of the slope of the graph, or the slope of the tangent line. But we could also think of the derivative function as the instantaneous rate of change of the function f with respect to x. Okay, so we could think of derivatives in terms of slope, or slope of a tangent line, or in terms of instantaneous rate of change. And in particular, for this second interpretation, when f of t is the position of an object moving along a straight line, f prime of t describes the instantaneous velocity of the object at time t. And that was really the impetus for how calculus got started in the first place. When Isaac Newton essentially invented calculus, he was using it to describe the laws of motion. He was talking about position and velocity and acceleration. And he needed calculus to really talk about instantaneous velocity. So he essentially invented calculus over one summer. And here we are, like 400 years later, still using it.